Can you hear me? Hello?
Yes, sir.
Hear me? Okay, let me start. It is not my fault, it is IIT's fault with some accounts. Okay. Hey, still. You can hear me? Hello? Hello?
Yes,
Yes,
sir.
sir.
Something
Yes, sir.
problem is going on here. I think Saturday है ना जो computer center, I think not too many people are taking care of that. Okay, let me do that. Okay, let me start. Okay, first let me give you some tutorial problems.
Sir, your screen is not visible.
My screen is not visible?
No, sir.
Oh, I understand what happened. मैंने वो ये नहीं किया. अभी विजिबल है? नहीं. एक मिनट.
No, sir.
No, sir.
अभी विजिबल है?
No, sir.
नो. अभी विजिबल है?
No, sir.
No, sir.
कैसे हो रहा है? ये तो आज तो बहुत प्रॉब्लम कर रहा है. पता नहीं क्या
There
हुआ.
is an option beside the leave button for sharing.
ये है तो पता नहीं कभी कभी ऐसा क्यों प्रॉब्लम करता है. ये भी तो मालूम नहीं क्या करना है. अभी अभी देखा रहा है?
No, sir.
No, sir.
तो क्या प्रॉब्लम हो रहा है देखता हूँ. आज बहुत ही प्रॉब्लम हो रहा है. I think I will join again and see that. Let me see that. Let me join again. Can you see it? No. Hello?
No, sir. No, sir.
Problem क्या हो रहा है? अच्छा, I will log out and then I will start again on that. I think there is some problem. ये सैटरडे लेना ही प्रॉब्लम है. एक मिनट देखता हूँ. I want to leave and then I join on that.
So it is visible now.
Is it visible now? Okay, let me see that. तुम्हें विजिबल है लेकिन मेरे पास तो स्क्रीन कहाँ है? मेरे पास तो अभी वही है. Let me see that. अभी विजिबल है?
Yes, sir.
हाँ, पता नहीं वो क्या हुआ. मैंने कुछ नहीं किया. ये लगता है वो कंप्यूटर सेंटर का प्रॉब्लम है कुछ. अरे मैं 20 मिनट से कोशिश कर रहा हूँ. Actually, the problem is that we have two email address. I am telling you that is Kundu at maths dot, that should be there. Actually, originally it was there, but now this is also valid. Is Kundu at the rate of math जरूरत नहीं है. But the problem is that I found that my laptop often makes a difference of that. Okay, so I was first trying to log in here, then it was not coming, then I did this, then it took up, and then problem, I think some computer center, they have some people that think they don't have somebody else. Okay. Now tutorial problem देखो. First, let me tutorial problem because Saurabh is working. It is Aliprant is working, sir. That kitab. Let me tell you that. I will just page. देखो 63 to 66 65 actually. Yeah. Abhi, not all the problems. Let me tell you. The first you will do problem number 1, 2, 7, 8, 9, 10, 11. From this, that last time I did by using NATE, that problem number 9. Last semester I did just without using NATE, but by using NATE last time we did it. Number 9. Okay, fine. And you should look at this at and today number 17. Okay. Now today look at problem number 19, 18, sorry. Page 65. It is talking about base actually. Okay, so let me first discuss the idea of the base actually. Base or basis? Base or basis for a topology. Suppose you have a topological space. Okay, now the question is, remember that tau is a subset of px, power set of x. So that do I have a smaller collection of that? This is a subset of such that here each member of tau is a union of some members of P. Look, arbitrary union of open set is open, so that it will be open. There is no problem with that. Usually we take the smaller collection. If you have this, it is trivially true. But the problem is that idea is that we want to have a smaller collection, so that instead of dealing with the whole thing, tau may be very big. I want to deal with the smaller collection. So if you have this, suppose this member of tau is union of some members of B, then B is called a basis or base. It's called a basis or base for topology. This is the idea. Look, in linear algebra we did basis because from the basis you can recover the every vector. So you need to deal with basically fewer elements, fewer vectors. Same idea is here. Like look at the simplest example. Look here, R with usual topology. When this is called usual distance or usual metric on this usual distance metric on usual, and the topology generated by is called the usual topology. Usual topology on R. Now look, but point is that if I take this, last time I told you that. About empty set, you do not need to bother about. You can take that empty set, but also you said that empty union over empty family is empty. Okay, so that don't make an issue of that. If you don't feel comfortable, you can add it. But look, this gives you the whole topology here, because any open set other any non-empty open set, I can empty open set nothing to do with that. Any non-empty open set can be in R, can be, suppose you call it P, can be written as a union of some members of, look, why empty set, if I take union of some members, if I take this empty family, then it will give you empty set. So that's why you do not need it. And in general, in a metric space, you see that if you have a metric space, you have the topology tau d. Okay, you have the topology tau d, and then you see that if you take all these balls, could take rational numbers also. From this you can recover any open set here. Any open set here. And last time I told you, any open set here can be expressed as a union of balls. You can make it a smaller collection, like you can take rational numbers, you can take reciprocal of natural numbers. Okay, so that means basically idea of the smaller collection of open sets. Okay, so that we can recover any open set, then it will be called a basis. Okay, now thing is that problem 18, if you look at that, okay, apparently look, he's taking topological space and taking this, of course, it's a non-empty family. For each x, so let me write it. Wait a minute, because I want to recover the open sets. Okay, so that for for any open set you can take non-empty. Empty open set you do not need to bother about. Non-empty open set, because for empty open set it will be vacuously true. Set V in x tau, that means in tau, in x tau, and x belongs to x, and for any x, and for any x in phi there exists b. Actually you should write it will depend on x as well as in v, so it should be like this, that I am writing using the notation such that we have this. Look, this is here, but this will depend on both x and v. So even if you take a fixed v, then it will depend on x. So that's why I'm writing that. The way they have written this is fine, but you should understand the meaning of that. Okay, if you have this, okay, right? Now if you have this, then again look what I was telling, why it is consistent. This is the same idea. So because if you take any v, so that right now for any x belongs to v, any open set, non-empty open set. So if you have this, so v is fixed. How will recover from that tuples? Then it will come like this. It is saying x, there exists bx. Bx belongs to b, subset of phi. Since v is fixed, I am using this notation instead of this. I am using this. Now again, like matrix space I did, you look, if I do this, union X belongs to V, union Bx, X belongs to V, but each of them is coming from V, so it will be V. But this is V. So you are getting V equal to, but each of them is here. So that exactly V you can recover from the family of open sets here. This would have been more natural than that. Any non-empty open set can be recovered from smaller collection from which you can recover all the open sets. Okay. Now the thing is, this is fine. Now he's saying that, look, the problem is giving, basically I'm doing this problem because this is a result on that, which is this is analysis book. That's why they are giving it as a problem on that. In topology books, they prove it. Now look, he's saying the B is called a base for this. In general, a collection of B subset is said to be a base. It is different direction. That I'm coming to that. Okay, so that the problem is what you're giving. Suppose, so base I have defined. Basically, X tau. So base is not unique. There can be many bases. Tau itself is the base for tau. So it is this that I told you, such that every member. Okay, so that here what is definition? The B is called the definition. The base. I'm giving the definition. Base for tau if given V belongs to tau and X belongs to V, there exists B, X, V belongs to B. If given this, there exists such that okay, let you should write let X tau be a topological space and non-empty family. This then B is called a base. Should write. For tau, if given V belongs to tau and X belongs to V, there exists such that you have this. Okay, this is base. So in a metric space, all the open walls, they form a base. They form a base. Okay. Now the thing is that I want to go in the other direction. What does it mean the other direction? What is the idea of the base? This is, you have the topology, you are finding a smaller collection of open sets which will give me the, from which I can recover each open set. That is fine. But in other direction, suppose you have this and I have this power set of X, and suppose you have a family here. This is not a topology. Suppose you have this non-empty family. Okay. Now I would like to have a topology tau. I would like to have topology tau on X such that B is the base for tau. The idea is that first of all, I want each of them member here to be open set. That means it belongs to some topology. But you can say that is not a big problem because I could take tau discrete topology. Then it will be, each of them will be open. Okay. So the largest topology is always there. So that's not a solution. Basically, I want a nice topology, not too big, not too small. Okay. In fact, I would like to have the smallest topology containing B, smallest topology, because then any other topology containing that topology will also contain that. So basically problem lies down to that the smallest topology containing because any other topology which contains this topology that will contain B. So that how to do that? Is it possible always? That is the question first of all. Okay. Is it possible? Always. Or else B should satisfy some conditions. Look, what conditions should it is not always possible because some necessary conditions there, and those who will say that they are sufficient also. But what is the necessary condition? First, look, if you want to have a topology tau which contains B, then what? X itself belongs to tau. I am having base, so X should be. I should be able to recover X as a union of some members of B. That means there exists something B naught contained in B such that X should be like this. Okay, some family, it may be the whole family. In particular, I should have this. Since for this I'm saying so this is one necessary condition. Unless you have it, you won't have it. Like in R, you see, if I just take two sets like that, you can say this, or they won't be a base because they won't cover the whole thing. That means members of B should cover the whole X. So these two won't give me a base for the usual topology on that. Okay, because it won't cover. The first thing, this is a necessary condition. You must have it. Okay, that's the first condition. Second condition, I'm saying the necessary condition. You look, what else? That will say together they will be sufficient. That now look, what is that condition? Suppose you have two members here. In B. Then look, first of all, you are having the topology, then B1 intersection B2. It may not be in B, but it will be in tau. Talking about the topology containing this tau. So that, but now I am saying this is also base I wanted. So it belongs to tau. That means if you have any points here, now I should have a member given this. There must exist, that is the question, Bx in B such that I should have, because if there is a topology tau containing this, then this will be in tau. Then I'm saying this is a base I want to claim, that I'm trying to claim, and then I should have it. So this is also necessary condition. The good thing is that these two necessary conditions together give a topology for which this is a base. That is the problem. The second part, he is defining what is called a base. Okay. In general, a collection B of subsets of a non-empty set, let me write that. So that, look, don't confuse. You have X tau and then I have given the definition. This base, it's a base for tau. Okay, This is you are starting with the tau topology. You are having a smaller collection. That is called a base. Now in the other direction, if you have X, you have this. Okay. How to get? The question is that how to get the topology tau on X such that P is a base for tau. But then you need some conditions to satisfy it. So here in this problem, they are giving basically this is necessary and equivalent conditions. Okay, so that the condition is that B will be a base, this is a result. B will be a base. That's the problem that has been given. Will be a base for a will be a base or basis for a topology tau on X if B satisfies one. Yes, that union of P belongs to P is X. Sorry. And 2. This is a result. And 2 this. For every pair AB belongs to this. For every pair AB belongs to P. Okay. B and this intersection X belongs to A intersection B. I previously took B1, B2. Okay. There exists some, that means C belongs to B such that X belongs to C contained in A intersection B. If you have this, it will give you a topology, and for that it will be a base. And then point is that it is a base topology, but then next thing they're saying that how will you get the open set? That means this is called the then it will be a base for topology. Then that is a B is a base. Is a base for a topology tau on X, and this is called, it will be unique actually. So you can write the called the topology generated by P. It's called the topology generated, and also why it is called generated. Like remember in linear algebra, when you say that some collection of vectors, it generates a subspace. So that is the smallest subspace containing that collection. Similarly here also tau is the smallest topology here A, I'm saying the to be unique is for topology. Smallest topology on X containing this. That is the thing. That's why it is coming down. But the point is that you may wonder, I have not said what members will belong here. Well, members will exactly belong here the way I got the definition of base. That means it will that exactly saying that gives a topology and for which it is a base. Look, So that if B is the base for a set X, then the collection, look what collection it we are taking. B subset of X, then it should satisfy the condition, the basis, that exactly the thing you're telling. Then for all X belongs to V, there exists B belongs to, look, it will depend on V already you have taken all those V subset of X, so it will depend on X. So you should write this, there exists Vx belongs to B with this. That means all those V satisfying these conditions will be the members of tau. Okay. For all X, I am writing specifically that it will depend on X. With it, we have this. Okay, right? Then it will be a base for a topology with B as a base. That you should prove. Okay. So this problem gives you the how to get it. This is the other direction, that given a collection of sets, some subsets of X, whether it will generate a topology. Okay, that won't generate a topology all the time. That is in first you was giving the necessary conditions which are sufficient also. Two conditions. And then they are saying how to get all the open sets. Okay, that way you get a base. Reason is like linear algebra problem. I start with this. Look, I would always try to have smallest topology because biggest topology is there, discrete. That won't help me, but this will help. So that I wanted you have this. And I want a topology here. I want to fill up this such that B is a base for tau. Reason is then I am getting a topology. These members are open, and for all the members of tau I can recover from B. Okay, right. Now look here. Suppose you didn't have it. Now look for the usual topology. If I take this, whatever, you can take Q anything that. Now this will the conditions there of those, huh? And that will give a base for you can topology, and then you can check that will be the usual topology. You can come the other directions. Now why I'm doing it? Now suppose I said I would like to have a smaller collection. Look here, if I took this, that will be this will be a base for the usual topology. The base of the usual topology on R. But the thing is that advantage is that this is countable because this is basically Q cross Q and both are countable. So this is countable. So it is a countable family. समझ गया? That means usual topology has a countable base. Look, don't confuse the local base. This is global base because here I am dealing with, I am trying to recover all the open sets. So this is called, you should understand this is a global base, not local base, not local base. But from each global base, I can have a local base. That I will show you that. So that smaller collection countable. Now the question is that some topologies will have countable base, some topologies won't have. Like usual topology, you have this. On the other hand, if you take this X, this is a discrete topology. This is uncountable. Take discrete topology. Look, it doesn't have a countable base. Does it have a countable base? It doesn't have a countable base. It does not have a countable base. You can easily check that why it won't be countable based on that. Okay. Look, look, if you have, how will you do that? Okay. Let me tell you, it does not have a countable base. Well, there are many ways to prove on that, but you think about it, it does not have a countable base. Okay. So that if you have a countable base, that's a very good thing. The space is very nice actually. Space is very nice actually. Okay. Now, so that let me, given through base, I can define topology. And let me see whether it will have a countable base or not. Now I want to see that. I will come that. If you have got a countable base, it's called second countable. That I will come later on. The now Sargent-Frey line. Look here, X is R. Okay. But basis you are taking now the basis. Look, A, B. This is closed. A, B belongs to R, A less than B. Okay. Look, this is a base. This will give us, you should check. This is a base for a topology. If you want, you can take this, or else you can take empty union. Union over empty family. Base for a topology. Usually people don't take that. Topology is a base for a topology tau on R. Look, since here, look, here I am having the lower limit. The upper limit is not there, though B doesn't belong here. So it is also called the lower limit topology. Lower limit topology on R. It will be a topology because the conditions I have given, you can easily check that R will be this. All these, to take P, then don't need this thing. A, B, sorry. Okay, this thing R, and if you take two members here, look, A, B, intersection C, D. Look, if their intersection is empty, nothing to prove. Okay, so you take this thing. Now look, what will you do? Okay, look, choice is that X can be A, X can be C, X can be none of them. Okay, right? But then what else you need? That X, look, I have X delta. What will be the delta? बताओ मुझे. बताओ. What should delta I can choose? I have B minus A, D minus C. I think I can choose delta half of this minimum. Sorry, wait a minute. Choose delta, 2 delta equal to choose minimum. Will it work? It should work. Actually, you can look at that. What else is? If it doesn't intersect, there's nothing to prove. So suppose this is A, B, and suppose this is your C, D. Okay. So basically, this, if you have this, you can take X as C here. Okay. And you have X here. Okay. What will you take X? Look, you have the intersection. That means intersection will be here only. This part. Okay. And I have taken b minus a, t minus d 2. I don't know where you can see that. What will be that? I have taken that. It may be not work, but you need something else. But basically this one, that is there. Okay. So that is there. I have taken so that you can see that. Actually, you can have this. Suppose you assume a less than c. That we have assumed here. You can similarly assume that same thing will be there. Okay. Then you can check that. So this will be a base. So that it will be a base for topology, and that topology is called the lower limit topology or Sargent-Frey topology. Okay, a Sargent-Frey topology. Got it. In fact, and R with this topology is called also the Sargent-Frey line. When you say real line, actually you take real topology, that usual topology. When you take a real line, then if you don't mention anything, then you take the usual topology. Look here, both set is a R. But when you take, say, Sargent-Frey line, that means you are taking R with this topology. Okay. Now look what else you are getting here. Okay. First, look for at any point x, if I take this x plus 1 by n, this is the local base at x belongs to R, local base, but this is countable. So that means R tau is Sargent-Frey topology, lower limit topology. Is first countable. Okay. 2, it is separable. Again, Q is dense here. In this topology, again Q is dense, it is separable. But it doesn't have a countable base. Now let me tell you, after I defined the base, okay, so that you take this definition. A topological space x tau is called second countable. We write this actually. You should write in the word second, because already we have defined first countable. The second countable if tau, basically x tau, has a countable base. Has a countable base. Okay. Second countable. Look, R with the usual topology is second countable. That already I told you why is second countable. Because if you take A, B, A less than B, AB belongs to both rationals. This is a base for the usual topology. And this is countable, is a base for the usual topology on R. Okay. This is Sargent-Frey line. Sargent-Frey line another has nice properties that we will discuss later on. But why suddenly I brought Sargent-Frey line? Because I gave the problem to Give me a first countable space which is not a metric space. Now look, the Sargent-Fay line is not metrizable. That means its topology cannot come from a metric. Sargent-Fay line is not metrizable. That means its topology doesn't come from a metric space. So this is an example of a first countable space which is not a metric space. But how to prove that is not metrizable? In fact, you do it indirectly in the sense, look here, first result, you see that every second countable space is separable. This is true for any topological space, is separable. Actually, proof is very simple. Let me keep this. Actually, this is the problem Ali Francis Perkins has given. Problem number 19. Read that. Okay. Separable. Okay. Now, okay, that instead of proving that what problem number 9 they are proving, let me tell you. Problem number 19. He's saying, so this what is 19, it can be proved as a corollary. Now look, what is saying, suppose this 19. Let X tau be a topological space and B be a base for tau. Then there exists a subset D of X, saying dense such that I have this 1, D is dense, and 2, cardinality of D is less than equal to cardinality of B. Look, if you have this, then if you have a countable base, then this will be countable. So that means this will be separable. Got it? Okay. So this is the thing. This is a corollary to that. If P is countable, then D is countable, but D bar equal to X, so X is separable. Proof is very easy. Look what happened. Actually, indirectly we'll be using axiom of choice. So suppose B is a base. So from each B member you choose, given B belongs to B, given choose members of B, you always take actually non-empty set. That's why I said don't take the phi. It will become always come. Choose XB belongs to B. Okay? And then you take this as D. Look, if you have D to B, you're taking this. Sorry. XB, you're taking this B. Okay. If this is 1 to 1, then cardinality of D will be, look, what will be the cardinality of D? Whether this will imply, I'm leaving it to cardinality of D says cardinality of B. Okay, right. So this is basically you're picking up this, but you'll have to prove that cardinality of D actually is less than equal to cardinality of B. Okay, right. Actually, it is easy to see that because if it is 1 to 1 still, look, if it is 1 to 1, if it is 1 to 1, let me tell you, if it is 1 to 1, then D, we will have a copy of D. Then the D, if 1 to 1, then cardinality of D will be cardinality of, suppose you call it whatever function, F. Cardinality of Ft. Okay, right? It's 1 to 1, but Ft is a subset of B. Any subset, if you have A subset of B, then obviously cardinality of A will be less than or equal to cardinality of B because you have the inclusion function. So this is cardinality of P. Okay. But if it is not 1 to 1, you should understand that the cardinality cannot increase via maps. It can only remain same. It can only remain same, or it can decrease. So actually, even it is not 1 to 1, cardinality of D it is actually uses axiom of choice. It is a problem in Alipratis and Arkansas. Last semester I gave you that. This will be always true. Okay, and FD is a subset of this, so it is. What I am saying this, suppose you have a function from x to y in Yang, then cardinality of fx will be less than or equal to cardinality of x. You'll have to come other way choosing, and that you need axiom of choice. I can tell you that what problem it is there. I think it is somewhere there. They gave an exercise. Let me tell you that.
Is this why?
I am just looking for the axiom of choice in the. You do remember the problem. I am just want to see that. I want to mention that problem. That this will be true, and you'll have to use axiom of choice. And I'm just looking at. I just to mention the problem here. That I'm trying to find out. Wait a minute. I think yes. Look, problem number in this book. Problem number 5A. In fact, you will need B actually. 5A, page 13. In fact, for every second countable space is separable, you need 5B actually. Okay. Right, that exactly. There it gave F A to B, and cardinality of B is less than or equal to this. Actually, subjective is saying that's onto. That's why he is putting this. So this is the problem. Okay, so that means image will have always cardinality less than or equal to that the domain. समझ गया? Okay, it can't increase. The map cannot increase the cardinality. Either it will remain same or it will decrease. Okay, so this way that you have got that problem, and so that if you have second countable base, so it will be separable. Is it all right? Huh? I'm doing cardinality topology, point set topology. Unless you have some basic knowledge of cardinality, you will have problem, because topology, many good properties depend on cardinality also. How big is the set? Okay, so that here again I'm telling you that this thing result, every second countable space is separable. Actually, more generally, you can prove this. So that if B is countable, so this is countable. Now, if every second countable is separable, okay, but a separable metric space need not be separable. Sorry, separable topological space need not be second second countable. But let me try this. Warning. A separable topological space need not be second count. Actually, Surgeon-Fay line is the most celebrated example of that. The Surgeon-Fay line, and its proof is not difficult. That I am leaving it to. If you can't do it, in Moncrief he has given the proof. You can see that Surgeon-Fay line is separable, but not second count. Exercise, prove it. You can ask Saurabh, you can try yourself. Proof is not difficult because here the problem is that you are having this thing, lower limit. That is the problem. Okay, so that makes the problem. Why it won't be second count? But still, you're saying why I'm still bothering so much about that? Because Surgeon-Fay line, because we will show that right now. That's the last result I will say. I will do today. If you have a metric space, then it has to be second countable also. Second countable. So that Surgeon-Fay line cannot be a metric space. Got it? But I have this result. A metric space xt is separable if and only if it is second countable. Look, one way is always true. So I need to prove if it is separable, then how to show that this is second countable. That means you need to show a separable metric space is second countable. Okay. A separable metric space is second countable. Look, in the ball, the problem is that if you have this, if you take all these balls, look, n belongs to n, but x belongs to x. But if it's uncountable, then it will be uncountable. But I want to replace this family where it will work with a countable set here. Okay, how to do that? That where it will come separable, it will come. Okay, right. Now look, how to prove that? Proof will be easy actually. And this will tell you the Surgeon-Fay line is not a metric space. It's a first countable space, but it's not a metric space. So that, look, what I'll do, let T be a countable. Actually, you can write D equal to this, be a countable dense subset of X. This I can have since it is separable. Okay, now look what I'll do. I'll take these balls, but be careful what I'll write. Xn, not same n, you'll write M. This you will take. Look, this is countable because n, this is basically the product of these two spaces. Okay, so this is countable. Okay. All I need to check, this will be base for this metric space. That all I'll have to check. Okay, fine. How to check that? Okay, for check, look, now we'll have to go to the definition of the base. Okay, that means if you have, because of पीछे था. Well, remember the definition of base and that. If you have any open set V, any open set V, and if you have X belongs to V, there exists a member in this such that you have this. For any open set V and any point in Vx, you have this. V belongs to the base. Okay, right? So actually, so that you take, let XD, separable matrix that you have taken. So take an open set V here and X here. But first you get this, there exists R greater than 0 such that I can take the second I will take X belongs to V. V is open in here. Open. V open. So there exists N belongs to N such that this I can always do that. ठीक है? Got it? If you have any R, you take an N, choose sufficiently large so that 1 by N less than R. Okay, right. Now, but now I will go there. Okay, right? Now look, remember that. What dense means that? You can write a dense set. Dense set. Suppose you have a topological space. Don't confuse with that. D is dense. Then d bar equal to X, I can write if and only for every open set, if and only if D intersection V not equal to phi for all V belongs to top. Got it? This is simple. This I think one of the problems I have given aside. D will be dense if and only if every non-empty set intersect for all V belongs to non-empty open set. Okay, na? Because if it is empty set, then it will be empty. Okay, for all non-empty. Okay, this is true. You can prove this is just a definition of density. That every point is a closure point now. So if you take a non-empty open set, so if you take non-empty set and every point is a closure point. Okay, every point. Suppose this way you are going. This way. So every point is a closure point. Okay, so that X particularly is a closure point and it is an open set containing this. So that D intersection V will be non-empty. Okay. And this will tell you that each point of D is a closure point. Sorry, each point of X is a closure point of D. Okay. So this is another way of saying that each point of big X is a closure point of D. That exactly you need. That you should understand. This statement means each point of X is a closure point of D. And this is another way of saying that. Okay, that each point of X is a closure point of D. This is another way of saying. So these are two same statements. So if you have this, why I'm doing this? Because this D previously I have taken this. Don't confuse with that. Don't confuse it. You should not use the same N. Okay. Since D is dense, so D intersection It's non-empty. Okay, right? If you want, that I will see that whether I need to manipulate further. But then means don't take same in. So xm belongs to this. Okay, got it? Now you see that xm belongs to d, xm belongs here. So that ax belongs to this. I am interchange ready as you look. Okay, got it? Now all I need to check that whether this is true. Look here, I will see that. कहाँ से आ गया अरे भाई? Let me see. So this I am getting. This is a member of that countable base I countable family I formed. Mn natural numbers. All I need to check whether this is true. Then this will be true. Well, you people should do that. You say it may not be true. Then what else I need to do? Okay. Right? Look, this I will get. Then you can take 1 by 2n. Okay? 1 by 2n. Now you can check that. It will be true. You'll see the trick. Okay. So this will be. You should check that. This is a triangle inequality. Okay. That I was telling you that at that time, that I will see that later on where I need to do the manipulation on that. Okay, right? I don't know still if you need it, but you should check. Okay, so this will tell you, look, this is the member of that family, the countable family. So that every separable metric space is second countable. Every separable metric space is second countable. Make sure that you complete the proof. Okay. Look, make sure you complete the proof of the every separable metric space. Sorry, that we got. Every separable metric space there is another concept, Lindelof, that I will teach you later. Every separable metric space is second countable. Every second countable space is always separable. So this is an important result. And Sargent-Fay line, look, I have given already too many exercise. Sargent-Fay line is separable but not second countable. The second thing I have given you an exercise. Make sure that you do it. Before asking Saurabh, I already gave you the hints. So you see that how to use that. You start with a contradiction. Suppose you have got a countable base on that. Okay. What will happen on that? It's very simple actually. Second countable. So that Sargent-Fay line is not metriizable. That means its topology cannot form from a metric space, not metriizable. That is, it is not a metric space. That means here is an example that often in the interview, for whatever purpose you give, if you say you are interested in topology, they will ask you this kind of questions like that. If you talk about first countable, suddenly then you say, can you give an example of a first countable space which is not a metric space? So this is first countable not a metric space. समझ गया? Make sure that. That's why I talked about Sargent-Fay line. In fact, it was, I think, his PhD thesis, 1946, if I am not wrong. Okay. So that's why Sargent-Fay line is answered many questions until then unsolved. Okay. That's why his the problems, his results are very important on that. They mainly work as counter examples. Okay. So it is not a metric space. So you should do it. Fine. Now look what I have taught you. Just let me give you a summary. So that when you look at, re-listen to my talk and whatever you should read from a book, and that you should read that what I taught actually. First I taught the base. What is the definition? Okay, right? And for corresponding to that came countable base. First you are having here, you are having a topology and you are having the base. When it is called a base. When called a base. Okay, this is the direct way. You are starting with a topological space and you have a smaller collection of this, and usually look, tau equal to b itself is a base, nothing to prove actually, but we always look for a smaller collection. Second, the other direction, opposite direction, to start with this when p is a base for a topology, tau on x. That's the problem number 18, or I think 18 or 17. 18. Okay. Not always. Must satisfy some condition. Not always. Problem number 18. In fact, what is the importance of that? Importance, look, Sargent-Fay line, we have not given the whole topology first. We have defined a basis actually. And then you can define the topology this way. I will call an open set if this happens. Okay, right? So that in order to define, this importance is to define topologies. Okay, right? So this is the importance, that to define. Often we do not need to define. We don't go for definition of all the open sets. We usually define a base and we see that whether it will be a base. That's why you should need to have those two conditions. Okay, at Sargent-Fay line implies that. But once you know it's a base, you know how to get the open set. So that Sargent-Fay line, you can say that. How will I declare a subset of R to be open in Sargent-Fay line? Okay, let R here now Sargent-Fay topology. How will I define? Okay, I will say let be this. Then P is called open in tau if given a given, that is for any x velocity, given means any, there exists r greater than 0 such that given x belongs to E. First you are taking a subset and then you said for any, it means for any. For any x belongs to, there exists r greater than 0 such that you have this. Okay, that's the way you are defining open sets. Okay, Once you know base, this is the only way you define open set. So surgeon-Fay line is important. Make sure that you understand surgeon-Fay line, because there will later on we'll talk about surgeon-Fay plane. That also works as a counter example. Okay, so make sure you understand surgeon-Fay line. And the main result I told you that a metric space is separable if and only a second countable. Because of that, surgeon-Fay line is not a metric space, but it is first countable. Okay. But you should check that, prove that surgeon-Fay line is not second countable. Okay. Any question? I think this much is all right. I have only talked about basis on that. Let me take this whether you have any other problem here. That 18, 19 तो you will do it. Question topology I will teach later on. ठीक है, अभी यही ठीक है. Okay, right? So I will meet you on Monday. Fine? Okay, bye. Okay, see you.
Thank you, sir. Have a good day.
ये प्रॉब्लम पता नहीं, मुझे देखना पड़ेगा क्यों प्रॉब्लम हुआ है ना. आज बहुत प्रॉब्लम हुआ. अभी भी ज्वाइन है, क्यों ज्वाइन है? लेक्चर 5 में क्यों?